In this video, we will discuss a few problems on fluids and pressure. In particular, we will present a few problems on pressure calculations involving systems such as manometer and barometer. We will also see how to evaluate water pressure exerted on a diver at a certain depth. Problem 1. The liquid in the open tube manometer. So this arrangement is called manometer. So the liquid in the open tube manometer is mercury, the density of which is 13,600 kg per cubic meter. Y1 is 3 cm and Y2 is 7 centimeters. Let the atmospheric pressure be 1.013 times 10 to the power 5 Pascal. Calculate the pressure at the bottom of the U-shaped tube. So let's do part A. So you want to determine the pressure at the bottom of the tube, represented by that line right there. So the pressure at that level inside the tube is given by two terms. The first is the atmospheric pressure, which is the pressure the atmosphere exerts on the surface of the mercury right there. And the second contribution is pressure due to this mercury column with a height of Y2, which is 7 centimeters. And that is given by the density of the mercury, gravitational acceleration, times Y2. So when you add these two terms together, you get the following for the pressure P. Atmospheric pressure is given as 1.013 times 10 to the power 5 Pascal, plus the density of the mercury is 13,600, gravity is 9.81, and Y2 is 7 centimeters, so in meter it will be 0.07. So when you compute this, you get the following for the pressure P. 1.106 times 10 to the power 5 Pascal. So that's the answer for part A. I'm going to denote this pressure with a subscript B so that I can differentiate this pressure from the pressure P inside the container, which we will evaluate in part C. Part B. You want to find the pressure in the open tube, which means in this side of that U-tube, at a depth of 4 centimeters below the free surface. So 4 centimeters below the free surface, that means right there. So what is the pressure along that line right there at that depth, the depth of 4 centimeters from the surface of the mercury? So again, the pressure at that point, let's denote it as P subscript 4, equals to the atmospheric pressure due to the atmosphere pressing on the surface of the mercury plus the mercury column with a height of 4 centimeters. So that would be the density of mercury, 13,600, times gravity, 9.81, times 0.04, which is the length of the column of the mercury. So this term right here is rho g h term. Using the atmospheric pressure of that value in here, so this will give you the following for P sub 4, and that's going to be 1.07 times 10 to the power 5 Pascal. Part C, the pressure P in the container. So what is this value P here? Whatever that pressure P is, that is the pressure that is pushing on the surface of this mercury on the left arm. So what is that pressure P? Now this point and that point are at the same level. So the pressure here, namely P, has got to be the same as the pressure here, which we have just computed in part B. And the reason is that because the mercury, the liquid, is in static equilibrium, pressures at points in the mercury at the same level must be the same. So for part C, the pressure in the container must be the same as the pressure at this point, which we had computed earlier, and that is 1.07 times 10 to the power 5 Pascal. And that completes the problem. Problem 2. The column in a mercury barometer, this is a barometer setup, has a measured height of 760 millimeters. So this H here is 760 millimeters. The whole apparatus is at the temperature of 0 degree Celsius. Thus, the density of mercury at that temperature is 13,600 kg per cubic meter. If the gravitational acceleration at the site of the barometer is given by that value, calculate the atmospheric pressure at the site. Note, the atmospheric pressure is the pressure at that level, and that must be the same as the pressure at that level inside the mercury. So all we have to do is to figure out the pressure due to the mercury column with length h. So we write the atmospheric pressure equals the pressure due to that mercury column. So the density of the mercury times the gravitational acceleration at that site times the length of the mercury column. The density of the mercury is 13,600. The gravitational acceleration is 9.80665, and h is 76 centimeters, or 760 millimeters. Converted into meter is 0.76. And that will give you 1.013 times 10 to the power 5 Pascal. So we say that the atmospheric pressure can support a column of mercury with height 760 millimeters or 76 centimeters. So oftentimes atmospheric pressure is also expressed as 760 millimeter mercury or 76 centimeter mercury. Problem 3. Determine the height of the atmosphere if the air density is 1.3 kg per cubic meter and the sea level air pressure is 1 atm. So the pressure here is 1 atm. So the pressure 1 atm is created by this column of air with a vertical height of h. So we say 1 atm is quite simply 1.013 times 10 to the power 5 Pascal, and that is given by the density of the air, 1.3, gravity is 9.81, that is gravitational acceleration, times h. So I am simply writing down the term rho gh, which is pressure due to air column of this much height. So h will turn out to be 7,943 meters. And that solves the problem. Calculate the weight of seawater on top of a rectangular area of 2,000 meters squared. So this area right there. So the area here is 2,000 meters squared at a depth of 250 meters. So of course we need to know the mass of the water that's contained in this rectangular block. So the mass is given by the density of water times the volume of that rectangular block. The density of water is 1030. The volume of this block is the area, which is 2000 square meter, times the height, which is 250 meters. So the weight is therefore is mass times gravitational acceleration, and that's going to be 1030 times 2000 times 250 times gravitational acceleration. And when you compute that, you're going to end up with 5.05 times 10 to the power 9 newtons. So that is the weight of the seawater that is contained in this rectangular block. Next, find the water pressure that a diver would experience at this depth. So assume that the diver is at that depth. What is the entire pressure that is acting on that person? The pressure due to that water column, that is. And that's given by the density of seawater, gravitational acceleration times the entire height of 250 meters. So the density is 1030, gravitational acceleration is 9.81, h is 250, and that's going to give you a pressure of about 2.5 times 10 to the power 6 Pascal. And to get the pressure in atm, all you have to do is to divide this pressure in Pascal by 1.013 times 10 to the power 5. And that will be 24.7 atm. And that solves the problem. Problem 5. Calculate the density of the oil in the left arm of the U-tube shown. Take the density of water to be 1000 kg per cubic meter. Let's take the density of oil that we want to calculate as rho naught. Now we want to compare the pressure. We want to write expression for the pressure on both columns at this level. And they must be the same. And the reason is because the entire system is in static equilibrium, and pressure at the same depth, for example of water, must be the same. So on the right hand side, the pressure here is given in terms of the atmospheric pressure and the oil column as the atmospheric pressure, PATM, plus the density of oil times the length of oil column, which is 140 plus 12.5 in millimeters. So that's going to be 152.5. Let's convert that into meter by dividing that by 1000 times gravitational acceleration. Now the pressure on the right hand side, on the right column, which means here, is again given by the atmospheric pressure that's present on the surface of the water, which is PADM, plus the pressure due to this water column, and that is the density of water, which is 1000, the length of the water column, which is 140 mm, converted into meter, so we divide that by 1000, times gravity. And these two pressures must be the same because they are at the same level. So the left hand side and the right hand side of the equation contains the atmospheric pressure, so they go away, leaving us with these terms. The left hand side and the right hand side both contains G, that's going to go away. Have a common factor, the conversion factor 1000, that's going to go away. And we end up with rho naught 152.5 equals 1000 times 140. And we can solve for the density of the oil, and that's going to be 918 kg per cubic meter. And that solves the problem. Thank you for watching.